Hey everybody, I want to talk to you about a kind of continuous probability distribution that we haven't used before, which since you clicked on this video, you probably know is called a T distribution. I don't know what the T stands for. Yeah, well, anyway, let's get going and see what T distributions are all about. So here's what they are. So a T distribution is meant to approximate a particular normal distribution, specifically N01, the standard normal distribution. So that's a mean of 0 with a standard deviation of 1. So T distributions, because they're approximating this particular normal distribution, they're very similarly shaped, but they're a little bit shorter and wider since they build in some extra uncertainty because they're derived exclusively from sample data. So instead of knowing the population standard deviation like you would for a normal distribution in the central limit theorem, we're not going to know that, and we're going to be using the sample standard deviation. And because of the extra uncertainty of using a sample rather than the population, we end up getting a wider, more spread out sampling distribution. Now, since it's derived from a sample, as n, the sample size, gets bigger, the approximation gets better. And we'll see that in a page or two here. So a term that you're going to be hearing a lot when we're talking about T distributions is degrees of freedom. And a degree of freedom in a kind of general sense is really just anything that can vary with it from sample to sample. There's a much more technical definition that we're not going to worry about. It's not relevant for us. For our purposes, degrees of freedom are just going to be how we identify which particular distribution we're using. So when we're doing T distributions, it'll tell us which T distribution it is. There are other distributions or other probability distributions or sampling distributions, both really, that use degrees of freedom, such as the F distribution and the chi-square distribution, that we'll get to eventually, and their degrees of freedom are calculated slightly differently, sometimes very differently. We'll worry about that when we come to it. For our purposes, for a T distribution, the degrees of freedom calculation is really simple. It's just the sample size minus 1. That's it. And since T distributions are approximating N01, which has a mean of 0, all T distributions are centered at x equals 0. And again, more degrees of freedom means they look more like N01, less degrees of freedom means they look less like it. So I've got a little, obviously not precision drawing here, but if this black distribution is N01, then T with 19 degrees of freedom is going to look a little bit closer to N01 than T with 10 degrees of freedom. That's all this is getting at. These are obviously not anywhere near to scale. T distributions actually approximate N01 much more closely than I've drawn them. They're not really this far away. I just drew it that way so that you could sort of see what I was getting at, which is more degrees of freedom mean better approximation. All right, so a thing we're going to be doing a lot is calculating a T statistic. That's going to be a thing that we need quite a bit, especially in topic 10 and going forward after that. But a more general thing that we need a lot is a standard error. So a standard error is just the standard deviation of a sampling distribution. So instead of saying standard deviation of the sampling distribution all the time, we're just going to say standard error. So the standard error in a T distribution is this. It's just S over root n. So notice that this is the exact same thing that we got from central limit theorem, where it was sigma over root n, except sigma is replaced with S, which is the sample standard deviation instead of the population standard deviation. So this is the way that T distributions are useful to us. We don't need to know sigma in order to know what the standard error of the sampling distribution is. And that's really important because it's actually unlikely that we would know sigma, right? We probably haven't taken enough samples of whatever we're working with to have a good sense of what the population standard deviation actually is. So it's likely, so this ends up being a very common thing but we don't know what sigma is, so we use S instead. And when we do that, we have to substitute a t distribution for the normal distribution. And yeah, that's what we end up doing with t distributions most of the time. Yeah, sorry, I lost my train of thought there. So your book calls the standard error of a t distribution, SEM for standard error of the mean. I had never heard that abbreviation before reading your current book. So this is not necessarily standard, but it's a fine abbreviation. There's nothing really wrong with it. And a t statistic, and this is a thing we're going to need a lot in topic 10, not so much in topic 9, but in topic 10 for sure all the time. T statistic is the number of standard errors the sample mean is away from the population. So if you guys know what z-scores are, which we haven't really talked about, but if you happen to know about them from another class, t-score and a z-score are basically the same thing. So here's the formula for a t statistic. T is x bar minus mu over s over root n. So x bar minus mu is just how far apart x bar and mu are in just absolute units. So right, if you're measuring this in pounds, then x bar minus mu comes out in pounds. Then what you do is you scale it to be measured in standard errors by dividing that distance between them by a standard error. So s over root n is your standard error. So this numerator tells you the distance between x bar and mu, and then the denominator scales everything so that it's all measured in standard errors. So this is your formula for a t-score. Now I bring this up because although I'm not a huge fan of using a lot of formulas in this class, the concept here of finding the difference between a couple of things and then scaling it to be measured in something inherent to the distribution is really common in statistics. This comes up just all the time. It's all over the place. So this idea of find how far apart things are, then scale them to be measured by something is really, really common. So I thought I would show you the formula for this. All right, so our main use for t distributions is to model the sampling distribution of the sample mean when we don't know sigma, which is normally the case. When we're doing some sort of honest to goodness research, it's unlikely we'll know what the standard deviation or the population standard deviation really is, because all we've got is a bunch of sample data. And when all you've got is a bunch of sample data, that's when your t distribution is useful. So let's do an example. All right, so here's my example. Jason's a marine biologist. He's found a new species of fish. He gets a sample of 11 of these fish, and those fish have a sample mean mass of 8.56 kilograms and sample standard deviation of 1.12 kilograms. So if it is true that mu is actually 8.8 kilograms, find the t-score of Jason's sample. Now, Jason doesn't know this. He would not be able to make this calculation because he doesn't know what the population mean is. But we can make that calculation for him, and then we're going to do B in just a second. So let me go to the next page. So I've got mu is, let's write this all in paint, right? So 8.8 kilograms, this guy is mu. 8.56 kilograms, that's x bar because it's his sample mean. And then 1.12 kilograms, notice this is S, not sigma, because it is referring to the sample. So that's how we're going to do our calculations. And N was 11, right? N is 11. Okay, so I've got all I need in order to find my t-score. So let's go and do that. So we get t equals. So it's going to be x bar minus mu over s over root n, which in this case, x bar was 8.56 minus a mu of 8.8 over s. Our s was 1.12 and our n was 11. So that's square root 11 there. And yeah, there we go. That's what we're going to calculate. I'm just going to go jam that all on a calculator. Where's my share? Calculator. All right, so we've got 8.56 minus 8.8 divided by s over root n, s was 1.12. over the square root of 11. And so our t-score is negative 0.71. Negative t-score is totally fine. All that means is that our sample mean was below the population mean, which it is. Right? Our sample mean was 8.56 and the population mean was 8.8. So we are to the left, and so we get a negative t-score. That'll happen half the time. Negative 0.711. Yeah, negative 0.711. Let's just go back. Ooh, just alt tabbing doesn't help. I need to switch this. So this is about equal to negative 0.711. All right, so we got a t-score of negative 0.711. Great. Let's see what part B was. If Jason wanted to take another sample of 11 of these fish, find the probability that this new sample would have a mean further from the population mean than that of his first sample. All right, so this was A. So in B here, we are going to need to draw our t-distribution. So on your t-distribution, everything is t-scores, not means. Everything in here, 0, and this is t with 10 degrees of freedom because our sample size was 11, so 10 is 11 minus 1. And we had a t-score of negative 0.711, so something like this, negative 0.711. So everything on the x-axis here in a t-distribution is a t-score. So that's why we have to find them in order to use our t-distribution. T-distributions, like I said before, are shaped like normal distributions, so they're still symmetrical. But they're a little bit shorter and fatter. Now, if you just saw like a wild t-distribution, you would not be able to tell it apart from a normal distribution. They just look the same. But they're not exactly. The formula is a little bit different for t-distributions. And by the way, I'm not going to go into what the formula is because it's a mess. It's significantly more complicated. It involves functions that you've probably never heard of, like the gamma function. And so we're not gonna get into what it is. So anyway, if I wanted to find the probability that Jason's next sample would be further away from the population mean than his first one, well, we're gonna do the same thing that we did all over the central limit theorem chapter slash topic, excuse me, central limit theorem topic. And we're just gonna shade in this area that's further away from the mean. And then we're going to use TCDF, which is just another CDF function in your calculator. Works pretty much like the other ones, very similar to normal CDF, except you don't specify the mean and standard deviation. You just tell it how many degrees of freedom instead. That's how you do it. So let's go to the calculator and do that. So I want to find this area that I've shaded in. Share calculator. All right, so we're going to go second vars, TCDF. Notice it's basically the same place. And then what we're going to have to put in is lower upper end degrees of freedom instead of lower upper end mu and sigma. So our lower value was minus infinity. Our upper value was negative 0.711. And the degrees of freedom was 10 degrees of freedom. Paste that in. There we go. Oh, I have to multiply that by 2 because I'm doing both sides, right? This is just the left side, so it's 0.2467 for one side. And so both sides together is 0.4933. So let's go back to whiteboard. So this was 0.24. So this area is 0.2467. Sorry, I'm doing everything in blue. I probably should have varied the colors a little bit. That's right. 4, 6, 7. And so all together, I end up with 0.4933. So 0.4933 is the probability that Jason's next sample will be more extreme than the one he just took. So about 50-50. All right, there you go. So that's t-scores and TCDF. Let's do this. There's an inverse t function, probably in your calculator, but well, if you're using the VMware, definitely. Which I'll show you how to find that. And then you can do the same thing with sheets in Excel using the t dot inverse function. So let's do the first one on the calculator. So the 75th percentile in the t distribution with 19 degrees of freedom. So we're doing that. Picture looks like this, 75th percentile. So this is T19. So centered at 0 here. 75th percentile looks like this, where 75% of the area is to the left of this number. I didn't label that 0.75. There we go. That's what I meant to do. Gotta get the hot pink in there so it contrasts nicely with the blue. And so the 75th percentile is that blue bar. So I'm going to use the inverse t function in the calculator to find that. So let's go over to calculator. So inverse t is found in the same place, it's in distributions. Inverse t is number 4 here, so 4. The area I want, it only does to the left. I don't know why. So if you remember from inverse norm, the VMware version of this calculator had left, right, center. I don't have that for inverse t. I don't know why, but if they don't have it, it means that they're going left. That their left is your only option then. So the area to the left of the number we're looking for is 75%. And I said 19 degrees of freedom, I believe. So we paste that in, there you go, 0.687. That's the number we're looking for. That, by the way, is a t-score. That's not like a sample mean or anything like that. It's just a t-score, t-statistic. So 0.688. So let's go label that on the whiteboard. So this is 0.688. All right, so for part B, I think I wanted like the middle 95%. Yeah, find the critical value, which is how many standard deviations you have to go. So its critical value is a t-score. For the middle 95% of the t distribution with 64 degrees of freedom. All right, so that picture is going to look like, there's my blue, there's my blue. So B, my picture this time looks like this. So we got, this is T64. Still centered at 0 because they all are. And then we said, I want the middle 95%. So this bit in the middle here is 0.95. And I want to know what the number of standard errors I have to go away from the mean to capture that much data is, which obviously this is very similar to the thing that we did in the inverse distribution function video. So I'm going to do the exact same thing, but I'm going to use t inverse or inverse t instead of inverse norm. Yeah, so let's go do that in Sheets just so you can see how that looks. Now, the thing to remember here is since this is 95% of the data in the middle, there's 5% on the outside, which gets split into 2 pieces. So this is 0.025 over here and 0.025 over here. So 2.5% on each side. So when I do inverse t, I'm going to be using 2.5% and 97.5%. So let's go share up our sheets. So this one, oh yeah, sorry. There we go, that's what I want. So this is going to be, so the function is t dot inverse. So equals t dot inv of, notice that it's formatted exactly the same, probability degrees of freedom. So we said 0.025 is my probability, my degrees of freedom was 64. And there we go. So my critical value here is negative 1.997 or just about 2. Now, we can do the same thing, and I will for the other side, but I actually don't really need to because it's just the positive version of that. But just to demonstrate that, equals t dot inverse 0.975 with 64 degrees of freedom, and lo and behold, it's the same thing, but with the positive sign. So you really only need to find the critical value one time, right? And that'll be and then for the other critical value, it's just the other, the other sign. So if you found the positive one, it'll be negative. If you found the negative one, it'll be positive. So this was, where'd my eraser go? Let's erase these guys. All right, so this was negative 1.998, I think, and this was 1.998. I know it was sevens, but I think it was like 7, 7. There we go. Those were the values. Those were the critical values that got me the middle 95% of the data in T64. Okay. That's all I want to say about T distributions. Let me just briefly sum up and then wrap this video up. So T distributions are approximations to the standard normal distribution in 0, 1. That's what they're for. We use them to approximate that standard normal distribution for our purposes pretty much when we're doing a sampling distribution, but don't know what sigma is, which is going to be the case most of the time in actual research. And we'll see a lot of that when we get to making confidence intervals, which is, of course, the topic that this whole thing is part of. We're gonna need these because we won't know sigma most of the time in those cases, and so we're gonna have to approximate the sampling distributions, a sampling distribution of the sample mean with a T distribution rather than a normal distribution. So that's what they're for. They look very much like N0, 1, but have some extra uncertainty built in, so they're just slightly shorter and just slightly wider, with the approximation getting better as n gets bigger. We identify the T distributions by their degrees of freedom, which is just n-1 for our purposes, right? So whatever the sample size is, -1, that's the number of degrees of freedom. They're all centered at x equals 0 and approximate at 0, 1. Yeah, I'll just go ahead and leave it there, and you guys can go back and rewatch whatever part of the video was unclear. And so I'll go ahead and stop the recording there, and I will see you guys in the next video.